Hey everyone, welcome to the Expressify Vibes. Our mission is to be the go to destination for tech enthusiasts. We aim to elevate your tech journey by providing engaging and practical insights, making each visit an opportunity to learn and be inspired.
For my first topic, I wanted to introduce you to large language models, abbreviated as LLMs, which have gained remarkable prominence as the most talked about subject in the industry. We will delve into understanding what these models are, their operational mechanisms, and the intricacies involved in their training.
What is a large language model? Simply put, a large language model is a type of computer program. It's a sophisticated piece of software that uses advanced machine learning techniques to understand and generate human-like text. Large language models have been trained on trillions of words over several months and with large amounts of compute power. The term large indicates the size of the model. A large model has a high number of parameters or weights, often in the tens or hundreds of billions.
What is a parameter? A parameter refers to the internal variables or weights the model learns during the training process. These variables are part of the model's architecture and are adjusted during the training process to make the model understand and generate human-like language. The number of parameters is an indication of the model's complexity and capacity to learn from data.
Larger models have more parameters and are capable of capturing more complex patterns and relationships in data. Due to their extensive parameters, they often exhibit a nuanced understanding of context and language, generating coherent text, performing language translation, solving complex problems, and performing a wide range of natural language processing tasks. Models like GPT-3 that has 175 billion parameters, Bloom that has 176 billion parameters, and GPT-4 that has over trillion parameters are examples of large language models. A small model, on the other hand, has a significantly lower number of parameters. While still being capable, small models may not capture as much complexity as large models. They might be more computationally efficient, but might not perform as well on certain intricate tasks. They can still be useful and trained to perform simpler specific tasks.
A large model requires substantial computational resources for training and inference. Training large models can be computationally expensive and time consuming. A small model generally requires less computational power, making them more feasible for certain applications, especially in resource constrained environments. The choice of the model, large versus small, really depends on the use case that you're trying to solve. Now that you know what a large language model is, let's look at how you interact with a large language model. Interacting with language models differs significantly from other machine learning and programming approaches. In conventional scenarios, you typically write computer code with specific syntax to engage with libraries and APIs.
In contrast, large language models have the capability to understand and execute tasks based on natural language or human written instructions, resembling human like interaction. The input you provide to a language model is referred to as a prompt. The area or capacity allocated for this prompt is known as the context window, and its size varies from model to model, typically accommodating a few thousand words. The result produced by the model is termed as a completion, and the process of employing the model to generate text is referred to as inference. Now, let's look at an example. In this example scenario, you instruct the model to determine what is at the center of the Milky Way galaxy. The prompt is supplied to the model, which then predicts the next words. As your prompt takes the form of a question, the model proceeds to formulate an answer. The completion encompasses the text from the original prompt followed by the text generated by the model. It is evident that this particular model effectively addresses your question by accurately recognizing the Milky Way galaxy and providing a sensible response that there is a supermassive black hole called Sagittarius A star. The text you input into the model is referred to as the prompt. The process of generating text is called inference, and the resulting text is known as the completion. The entirety of text, or the available memory for the prompt, is known as the context window. While this example illustrates the model's effective performance, it is common to encounter situations where the model doesn't initially produce the desired outcome. Refining and optimizing the prompts or input instructions may be required to achieve desired or improved outcomes. This technique is called prompt engineering, and it is an iterative process where users experiment with different prompt formulations to influence the model's responses. Prompt engineering is an important topic. Prompt engineering in the context of LLMs, such as GPT models, involves several key aspects. Here are some considerations when working with prompt engineering for LLMs. Language precision. This involves choosing clear and precise language in the prompt to convey instructions or queries effectively. Adjusting the wording may lead to more accurate or contextually appropriate responses. Contextual cues. This involves providing sufficient context in the prompt to guide the model's understanding. Including relevant details or examples can help the model generate responses that align better with the user's intent. Task specification. This involves clearly specifying the task or goal within the prompt. LLMs can be versatile, and specifying the desired task can enhance the model's ability to provide relevant information or complete a specific task. Length and structure. This involves experimenting with the length and structure of prompts. Some models might respond better to concise prompts, while others may benefit from more detailed instructions. Training on custom data. This includes fine-tuning or training the LLM on custom datasets related to specific domain or tasks. This helps the model learn context and terminology specific to the user's needs. Handling ambiguity. This involves anticipating potential ambiguities in the prompt and addressing them to avoid misinterpretations by the model. Adding clarifying details can enhance the accuracy of the responses. Temperature and top K or top P sampling. We will cover more details in upcoming videos, but for now, just know that we could adjust the temperature parameter to control the randomness of the generated output. Higher the temperature, greater the randomness. This also involves experimentation with top K or top P sampling to influence the diversity and quality of responses. Multimodal input. For models that support multimodal input like GPT-4, experimenting with combining text prompts with other modalities like images can provide better outcomes.
Prompt engineering is often an iterative process where practitioners experiment with different combinations of these aspects to achieve the desired results. It requires a deep understanding of the model's behavior and capabilities, as well as the specific requirements of the task at hand. Now, let's conclude this video by diving into a powerful strategy to get the model to produce better results. You can provide examples of the task that you want the model to perform inside the prompt.
This practice of including examples within the context window is called in-context learning, or ICL. Let's look at an example. In the provided prompt, you instruct the model to evaluate the sentiment of a review. The prompt comprises the instruction, classify this review, accompanied by contextual information, which in this case is the review text, and concludes with an instruction to generate the sentiment. This approach, known as zero-shot inference, involves incorporating input data directly into the prompt. Remarkably, the larger language models excel at this, effectively understanding the task and providing accurate responses. In this specific instance, the model accurately discerns the sentiment as positive. Here is an illustration of a completion provided by a smaller model. Noticeably, the smaller model deviates from the given instructions. Although it generates text somewhat related to the prompt, it struggles to discern the task details and fails to identify the sentiment. Introducing an example within the prompt can enhance performance, as demonstrated here. The extended prompt now initiates with a completed example illustrating the tasks for the model. After specifying that the model should classify a review, the prompt includes a sample positive review. I love this restaurant, the food was top-notch, followed by a sentiment analysis. Subsequently, the prompt reiterates the instruction and includes the actual input review for analysis. This comprehensive prompt provides the smaller model with a clearer understanding of the task and the desired response format. The use of a single example is known as one-shot inference. Occasionally, a single example may not suffice for the model to grasp the intended task. Therefore, the concept extends to few-shot inference where multiple examples are included. In this case, a much smaller model, initially unsuccessful in sentiment analysis with one-shot inference, attempts a few-shot inference by incorporating a second example, a negative review. Utilizing a mix of examples with different output classes aids the model in comprehending its task. The new prompts are presented to the model, which now comprehends the instruction and produces a completion, accurately identifying the review's positive sentiment. In summary, prompt engineering can guide the model's learning through examples.
While the larger models excel in zero-shot inference, smaller models can gain advantages from one-shot or few-shot inference, incorporating instances of the intended behavior. However, it's essential to be mindful of the context window as there is a constraint on the volume of in-context learning that can be fed into the model. If you observe suboptimal performance, particularly when including 5 or more examples, it might be advisable to explore fine-tuning your model, but that is a topic for another video.
All right, let's conclude this video by doing a quick recap of what we've learned so far. We started off by defining what a large language model is and talked about how the number of parameters determines its size. We then learned the differences between large and small models and how they can be applicable for specific use cases. Following that, we explored prompt engineering and the different considerations when working with prompt engineering for LLMs. Finally, we learned about in-context learning and saw examples of zero-shot, one-shot, and few-shot inference. I hope you found this topic insightful and engaging. I'll see you in the next video.